Hey guys, Alex here with Serious Goose Games. Welcome back to our Unity Tactics RPG tutorial. In the last video, we made sure our units snapped to the grid and made it so that they couldn't walk through each other. Today, we're wrapping up our unit movement with some A-star pathfinding. The code we need for today is pretty cool, but it's also kind of extensive, so if you need to pause the video, make sure you do so you don't get lost. The first thing we want to do is open up our tile script. Inside here, we need to add a few variables for pathfinding. The first one is going to be a public int. This is going to be our G cost, and this is going to be equal to int.maxValue. Next is going to be another public int. This is going to be our H cost, and by default, this is going to be 0. And then we need one more public int called F cost. And F cost is interesting because we're not actually going to store any values in here, but we are going to make it so when we use it, it's going to return some value. So we're going to do equal sign and then our chevron, and that gives us a little arrow. And then we want to return, whenever we call our F cost, we want to do our G cost plus our H cost. And the last little thing we want here is a reference to a tile, and we're going to call it parent. The parent is important because when we go and retrace our path, we need to know what tile we came from. There's more we have to do in here, but we'll come back and deal with that later. For now, let's hop into our grid manager script. And at the very top, we need to add a new namespace, and it's using system.link. Link allows us to do a bunch of fancy, interesting things with lists, and we're going to need that for pathfinding. Next, we need to create some helper functions, and because we're doing A-star, we need something called a heuristic, which is a good enough value. Basically, we can't actually figure out what the real distance is going to be, so we're going to estimate it. And because we're using a grid, we're going to use Manhattan distance. So down at the bottom, we're going to create a private int called getHeuristic, and we want to pass in a tile called start and a tile called end. And to get the Manhattan distance, we're going to return mathf.abs, absolute value, and we're going to subtract our x-coordinate and our y-coordinate and add them together. So start.gridPosition.x minus our end.gridPosition.x. And to that, we're going to add mathf.abs and do the same thing with our y-coordinates. So if I have a tile at, say, 2, 3, and another tile at 4, -6, and we pass those two tiles in, we're going to end up with -2. 3 minus -6 is going to be +9. And if we add those together, we get 7. That'll be our Manhattan distance between those 2 points. Next, we're going to create a function called retrace path. So we're going to create a private list of tiles. We're going to call it retrace path, and we're going to pass in a tile called start and a tile called end. So what this will do is we will do our pathfinding. We'll do the algorithm. We'll get a path, and then we're going to retrace that path. And because of how the pathfinding works, it gives us our path in reverse order. So we need to swap it around so it's the right direction. So we're going to do list of tiles called path. And this is going to equal a new list of tile. Then we're going to create a tile reference called current. And we're going to start this at the end. And then as long as our current is not the start tile, so while current is not equal to start, then we're going to do path.add current, and then we're going to set current to be equal to current.parent. So what this will do is once we do our pathfinding, once we do the A-star, it's going to kind of give each tile its checked a parent. So if we pass in the end tile and kind of work our way back through the parents, it's going to give us a nice path from end to start. But obviously we don't want to go end to start, so we're going to do path.reverse, and then we're going to return the path. Now for the pathfinding, there's quite a bit here, so we're going to do public list of tile. We're going to call it getPath, and we want to pass in a tile called start and a tile called end. We're going to start this out by creating a list of tiles called open. This will be equal to a new list of tiles. Then we're going to create a hash set of tiles called closed, and this will be equal to a new hash set of tiles. Now the reason we're combining the two is because lists are really useful for going through and getting specific things in order or sorting them whereas a hash set is really good at just checking if something's there. So we're using the list for open because it needs to be modified, changed, and sorted. Hash set because we just need a quick lookup of if we've already checked a tile. Then we're going to grab our open list and add. So open.add start. Then we're going to set the cost of our start tile. So start.gcost is equal to 0. And our start.hcost is equal to getHeuristic, start, and end. And then we're going to set start.parent equals null. Now, while our open.count is greater than 0, so as long as there is a tile we still have to check in our open list, then we want to grab a tile reference called current. This will be equal to open.orderBy, and we're going to do t lambda t.fcost. We're going to do dot then by, and then t lambda t.hcost, and then dot first. Basically what we're doing here is we are grabbing our open list and we are sorting it first by fcost. So we're passing in t for tile, and then sort it by fcost, then by hcost. So if they have the same fcost, then we'll sort by hcost, and then we'll return the first. So this little symbol right here is the lambda operator, and it's basically like a function. We give it a value and it returns some other value back to us. And it's nice because we don't need to write a whole new method just to handle that. It'll just do it for us. So lambdas are pretty neat, but my explanation, my ability to explain them is unfortunately slightly lacking. The next thing we want to do is if current is equal to end, and we're going to return retrace path, start and end. Otherwise, we're going to open.remove our current tile, and then we're going to add it to our closed hash set. And then we're going to do a for each loop. So for each tile neighbor in get tile neighbors, we're going to pass in our current tile dot grid position. So for every neighbor we get out of that, we want to check if closed dot contains neighbor, or if the neighbor is occupied, we don't want to factor it in. So if either of those are true, we're going to continue. So we're going to kind of skip this iteration and move to the next one. Next, we're going to create an int called temp_g. This will be our temporary gcost. And this is going to be equal to our current.gcost plus our neighbor.moveCost. Now we're going to check if our open list doesn't already contain neighbor. So exclamation point, open.contains neighbor, or if the temp_g is less than the neighbor.gcost. So if either of those are true, meaning we haven't looked at it already, or we've calculated a cheaper movement cost to get there, then we're going to grab our neighbor.gcost and set it to be equal to temp_g. Our neighbor.hcost is going to be equal to getHeuristic, our neighbor, to our end. And then we're going to set the neighbor.parent to the current tile. And then if open.contains neighbor is false, so if we don't currently have it in our open list, we're going to add it to our open list. And then at the very bottom of that, we're going to return null, meaning there is no path. So that's it for the A* pathfinding. And what we're going to do is save that, head over to our unit script, and we're going to add a new namespace using system.collections.generic. And then we're going to create a list of tiles. So public list of type tile, and we're going to call it path. And using that path, we want to adjust how we're handling movement. Inside the system, we are checking our distance. Underneath where we're setting is moving to be false, we want to remove the node. So path.remove at index 0. We want to remove the tile that we were moving to, because this if statement is saying we reached our destination. So we're going to remove that tile, and then we're going to check if our path.count is still greater than 0, meaning there's still more paths to traverse. Then we're going to do move to, and we're going to pass in our path at index 0 dot transform dot position, and then path at index 0 dot grid position. So this will make sure that we are moving to whatever tile is next in our path, or we are done moving. And it's going to keep on walking down that path until there is no path left to walk. We're going to hop back to tile and go to onPointerDown. And inside here, we're going to assign our grid manager as a reference that we don't need to call getComponentAndParent multiple times. So we're going to do grid manager, and I might move this up to be global later, but for now this will work. So we'll set that to be equal to getComponentAndParent grid manager. Now that we've got that, we can replace this here with Grid Manager. And now underneath that line, we can do player.selectedUnit.path is equal to Grid Manager.getPath. We're going to pass in Grid Manager.getTile, and that will be our player.selectedUnit.gridPosition, and then this as the end tile. After that, we're going to change this move to. So instead of having it just move to this tile's position, we are instead going to do player.selectedUnit.gridPosition. Now we want to modify our move to here. Instead of passing in this tile, we're going to pass in our player.selectedUnit.path at index 0. So the first tile in our path, .transform.position. And then for the second value, it's going to be player.selectedUnit.path index 0.gridPosition. So that done, go ahead and save your code. Now in order to better see this work, let's select our units, and we're going to set their movement range to be 7, and we'll save our scene. So now when I select a unit, I can move it, and instead of just gliding to it, it's going to follow a little path. You can see it's a little subtle. That one just glided right to it because that was the shortest path. But you can see how this guy kind of took this diagonal path, and that's because if I move up a bit here, if this unit here, which started here, wanted to get to where it is now, the cheaper path is to follow the road, or these kind of darker tiles, because these only have a movement cost of 1. So that is the shortest path compared to going straight across, which would have had 1 higher, because these light green tiles are 2 movement cost. So we can see that the A star is working. It is getting the shortest path to wherever we are trying to go. But for the most part, this wraps up our unit navigation and movement. There's still little things we have to tweak and change and, improve on, but this is kind of the core of it. Next time, we're going to start setting up unit stats. That will let us get into combat systems and get a little bit more going on than just moving cubes around. That's all for today, though, so if you learned anything from this video, hit like so other devs can find the series, and subscribe so you don't miss the next episode. In the comments, let me know, what are some scenarios, conditions, use cases where this A-star pathfinding is not going to work? Where could you see some complications getting involved? Anyways, thanks for watching. I'm Alex with Serious Goose Games, and I'll see you in the next one.